Well, hello there, team. Today we are talking about uniform circular motion. And we're going to jump right into it. Now, you don't really know what a record is anymore because you barely ever see these. But perhaps you know them because they are cool and retro. Well, here's a question. If I had a record... Oh, my circle was bad. Why did it just stop halfway through? Okay, that's not terrible. It's close. I'll take it. If I had a record like this and it was sitting on a turntable so that this record could be played. Now you'll remember, if you remember anything about these records, which are very retro, you'll remember that in order for a record to be played, you need a record player. And this record player, it's basically sits the little record down on the record player. The record player, the turntable, spins that record, and then a little needle falls down. That little needle jumps up and down along the little red ridges in the record, and that's where the sounds come from, is from the vibration of that little needle. So here we have a record. Let's suppose that on this record you had two little bugs who decided that today would be the day. What color should the bugs be? Teal. We're going to have cyan bugs. You have two little bugs who decided that today would be the day when they wanted to go on a little merry-go-round ride. And so one bug grabbed onto the outside of the record like this, and another bug grabbed onto the inside of the record like this, and those two bugs decide that today is their merry-go-round day, and they start to spin around with the record. And they hold on for dear life as that record goes around and around and around in circles. Well, here's a question for you. Which bug would be going faster, the outside-most bug or the inside-most bug? And you say, in order to answer that question, Miss Wilson, I would have to ask you, what do you mean by faster? Because the speed of the bug actually depends. There are two ways to talk about their speed, and the answer changes depending on how you talk about their speed. Today we're talking about uniform circular motion. When we say uniform just means going at a constant speed. Constant speed. And when we say circular, we mean going in a circle. So when we talk about uniform circular motion, we're talking about things that are moving at a constant speed in a circle. Like these two bugs on a record. When these two bugs are on a record, they're spinning around in a circle, but they're going at a constant speed. That record isn't speeding up. It's not going faster and faster and faster as it spins. It's not slowing down. It's not going slower and slower and slower as it spins. We're looking at uniform circular motion, which is what happens when an object is spinning in a circle at a constant speed. We're going to start today by talking about how there are two different ways to spin. Two ways to spin. That is a terrible spin. And to demonstrate this to you, the two different ways to spin, I'm actually going to go grab my football really quick. I'll be right back, 1 sec. Okay, I'm here and I have my football. I'm going to show you two different ways for a football to spin. The first way for a football to spin, if I told you to spin a football, then you might spin it like this. Whoa. Then you might spin it like this. And if you were to spin it like this, that's one type of spinning. The football is spinning around like this. But there's another type of spinning. If I asked you to spin a football, some people might say, okay, I can spin a football. And that is also spinning a football. Both of those two spins are both spins. And so they're both different types of circular motion. We give them different names. When a football spins like this, when it's spinning around an axis that is inside the football, we call that a rotation. When an object like a football spins around an axis like me, do you see that I'm the center of the circle at this point? When it spins around an axis like me, then it's spinning around an axis that is external to the football, and we call that a revolution. Here are those two words. Here are two words. We got rotations and revolutions. In a rotation, an object spins around an axis that is within the object. In a revolution, the object spins around an axis that is external to that object. I would highly recommend writing down those two definitions, and then after you do, ask yourself this question. Which one does the Earth do? Does the Earth rotate or does the Earth revolve? You say that the Earth rotates and revolves. You say, Miss Wilson, the Earth rotates on its own axis, and at the same time as it's rotating on its own axis, it is also revolving around the sun. And so the Earth does both rotate and revolve. Now that we've talked about the two ways to spin, take a look at these little bugs on the record. Which are these bugs doing? Are these bugs rotating or are they revolving? You say, Miss Wilson, they are revolving. Check it out. They're spinning around the center of the record, which is here. And so that's their axis of rotation. They are going around that externally. If they were rotating, then each little bug would be a little ballerina bug, and it would be rotating around an axis that's through itself. But instead, that's not what's happening. What's happening is the little bug is rotating or is revolving around an external axis. We've talked about two ways to spin. Now, there are actually two ways to describe the speed of an object that is spinning. And you can use these two ways to describe an object that is rotating, or you could use these two ways to describe an object that is revolving. We talk about two different types of speeds. We have what we call, number one, an object's linear or tangential speed. Or we can talk about, that's a terrible line. Or we can also describe an object's, when it's spinning, we can describe what we call its angular or its rotational speed. Okay, sorry, I gotta move my face. When we are talking about, oh my GOSH. Okay, when we are talking, let's go here. When we are talking about linear speeds, linear speed is just the ordinary kind of speed that you know and love. It's the speed that you represent with the letter V. But in order to distinguish this linear speed from like normal linear speed, in order to say that, hey, this is my linear speed when I'm going in a circle, I'm going to call it V subscript capital T, where T stands for tangential. You know from days of old that your average speed is equal to your delta x over your delta t. Well, these bugs are both going a certain distance, and they're traveling that distance in a certain amount of time. But we can be more specific when they're going in a circle. When they are going in a circle, let me change up my color here. When they are going in a circle, this little outside bug is going in a little circle like this. Well, that was kind of a circle. And this inside bug is going in a little circle kind of like this. Like so. If I wanted to talk about each little bug's linear speed, well, then I would say that the distance that this bug goes, well, each bug is going to go around the circle. So the distance that the bug goes is going to be the circumference of the circle. And we know that the circumference of the circle is going to be 2 pi r, where r is the radius from the center of the circle to where the little bug is. So for this little bug here, it's going to be, I'm going to call this r1, and for this little bug here, I'm going to call this r2. So each of them are going a certain distance, and the distance that they go is the circumference of the circle, and they accomplish that distance in a certain amount of time. And we say that the amount of time that it takes, we're going to define a new variable here, is going to be capital T. Capital T represents the period of the motion, and the period of the motion is essentially how long it takes to go in one circle. It's the amount of time for one circle. So we say that their tangential speed, the tangential speed of each bug, is equal to 2 pi r, the circumference of the circle that it accomplishes, divided by the amount of time it takes to go in that circle, which is the period t. This gives us a new equation for linear or tangential speed for an object that is going in a circle. And you can most definitely add this equation to your bag of tricks. Hey, as you add it to your bag of tricks, do you see that this equation is really just this equation, except that our distance here is the circumference and the time is the time it takes to go in a circle? The units here are going to be our same old ordinary units that they always are for speed, which is just meters per second. Now, let's talk about their angular speed. If I want to talk about their angular speed, well, there are two ways of talking about how fast they're going. One way of talking about how fast they're going is to talk about how much distance they cover in a certain amount of time. But another way to talk about how fast you're spinning is to talk about how many circles you can go in a certain amount of time. Isn't that a good way to talk about how fast you're spinning? If you do 7 circles in 2 seconds, well, then that's much faster than doing 3 circles in 2 seconds. So we can talk about how many circles that they accomplish in a certain amount of time, or we could talk about how much of a circle they accomplish in a certain amount of time. Did you accomplish half a circle, a quarter of a circle, 2/3 of a circle? And so the way that we talk in terms of angular speed is that angular speed is how much angle of the circle that you make it through in a certain amount of time t. Notice here, this is distance per time. Here, in angular or rotational speed, we're talking a change in angle in a certain amount of time. And that is equal to our symbol that we use for angular or rotational speed is the Greek letter omega. The Greek letter omega is kind of like the lowercase letter w, but that's how I write the lowercase letter w. Notice these are not the same. The Greek letter omega is a little bit swoopier than just the letter w, so when I write my letter omega, I make sure that it looks nice and swoopy like this. And there it is. That is one equation for angular speed. We say that angular speed is how much angle an object accomplishes in a certain amount of time. Now, let's talk here about units. You actually have 2 different units that you can use for angular speed. Your units can either be radians per second, because it's angle per time, or if you want to talk not in terms of how many angles you accomplish in a certain amount of time, but in terms of how many circles you accomplish in a certain amount of time, a lot of times we'll talk in terms of revolutions per second, where a revolution is just one time around a circle. So if your angular speed is 7 revolutions per second, that means you made it around the circle 7 times in 1 second. These are both acceptable units, but they kind of lend themselves to different equations. Let's take a look. If I wanted to talk about omega in terms of period, the same way that I talked about my tangential speed in terms of period, if I want to talk about my angular speed that way, well, I would say that t, capital letter T, that's the period, that's the amount of time it takes it to go around the circle once. And then the amount of angles in a circle is 2 pi. So omega is equal to 2 pi over t, 2 pi over the period. But omega, if I'm using these units here, omega can also be talked about in terms of how many times I make it around the circle in the period of time. And in one period of time, the definition of a period is that I make it around a circle 1 time in 1 period. And so this gives me 2 more equations for angular. Oh, wow, I just cut straight through the period. 1 second. I also did it again, so then I guess it's fate. Okay. Both of these equations give me ways of talking about the angular speed, but one I use when I'm talking in terms of how much angle, how many radians per second, and the other one I use when I'm talking about how many circles, how many revolutions per second. Now, if I asked you which bug is going faster, you would say, what do you mean by faster, Miss Wilson? Are you talking in terms of linear speed or are you talking in terms of angular speed? Go ahead and think for a quick second which bug is going faster in terms of the linear speed and which bug is going faster in terms of the angular speed. Take a minute, think it out, and then we'll talk about it. Okay, I'm assuming that you thought. So, if we talk in terms of linear speed, we would say that this outside bug actually goes faster in terms of linear speed. Why? Because he's accomplishing a big circle in the same time that the little bug, or that this bug, the inside bug, is accomplishing a little circle. So they both accomplish in the same amount of time 2 different circles, but the outside bug circle is bigger, and so it goes further. All track runners know this to be true. If you said who runs further, the kid that runs on the outside of the track and finishes, or the kid that runs on the inside of the track and finishes, if they ran the same amount of time around the track, they would say, well, the kid on the outside went further, and so they actually ran faster if they finished at the same time. When it comes to angular speed, check it out. both bugs actually accomplish the same number of circles in the same amount of time because they're on the same record. So they both, and you can think about it this way too, these two guys both move through the same amount of angle. So if this little record, let's say that this record is spinning this way, if this little record is spinning this way, they would both end up over here at the same time. So here's one little bug, here's another little bug. Wow, those are really bad bugs, but you get the idea. They both accomplished the same angle theta in the same amount of time. So both bugs actually accomplished the same angular or rotational speed. They're going to do the same number of loops in the same amount of time. They're going to cover the same angle in the same amount of time. Now, if you were on a merry-go-round and you wanted to choose the fastest horse, you should probably choose the horse on the outside because the speed that you're going to be feeling most of the time is going to be your linear or your tangential speed. So the outside horse actually does move faster than the inside horse because it covers more distance in the same amount of time. But if you are looking at your angular speed, then both horses, the outside horse on the merry-go-round and the inside horse on the merry-go-round, they both have the same angular speed. They both accomplish the same angle in the same amount of time. They both accomplish the same circle. Or they both make it around the circle the same number of times in the same amount of time. Now, both of these different types of talking about linear speed and talking about angular speed, they can both be useful for very different reasons. 1 second, I know I keep pausing it, but I have to go get my record. 1 moment, please. Oh, gosh. Let me try again. 1 moment, please. Okay, we're rolling. Okay, one of my teacher friends did give me this record one time. I've never once heard any of the songs on it, but it's kind of okay because the songs are Rudolph the Red-Nosed Reindeer and Joy to the World and Deck the Halls, so I'm not feeling like I'm missing out on too crazy much, but I've actually never played it before. Now, the way that a record works is that a record has to tell you on the record exactly how fast you should spin it when you put it on the turntable, because if you spin it too fast, then the song will be too fast, and if you spin it too slow, then the song will be in slow motion. So, our records always tell us exactly how fast you should be playing the record. Now, here's a question. Would you rather the record tell you the linear speed for playing that record or the I almost said linear tangential, which is the same thing. Would you rather the record tell you the linear speed for playing the record or the angular speed for playing the record? You should say, I would rather it tell me the angular speed. And the reason why is because doesn't a record actually have lots of linear speeds depending on where you're standing? Right here, it's going to have a smaller linear speed. Here, it's going to have a slightly bigger linear speed. And here, it's going to have an even bigger linear speed, all depending on your radius away from the center of the record. But it's only going to have one angular speed, and the whole thing is going to turn together. It's going to turn through the same amount of angle in the same amount of time. So my record here says, if you look on there, it says that you should play this record at 78 RPM, where 78 RPM, that RPM stands for revolutions per minute. 78 revolutions per minute. Here's a question for you. Could you figure out how fast a bug would be going? If a little bug came onto my Christmas record and sat on the very edge of the record and spun around with the record, how fast would that bug be going linearly if that record was playing at 78 RPM? Well, let's try this practice problem. 1 moment, please. Wait for it. It will be here soon. Pretty soon I'll get a new drawing. Here we go. It's all happening so soon. Okay, actually, I'm going to go to green because that feels Christmassy without being aggressive like red. Okay, here's what I know. I know that the angular speed of my record is 78 revolutions per minute. I also happen to know that the radius of my record, because I measured it earlier, is 12.4 centimeters. So if a bug was sitting on the very outside edge, they'd be sitting 12.4 centimeters away from the center. Now here's a question, is how fast would that little bug be going tangentially or linearly? To answer this question, before I do anything, I'm thinking I'm probably going to want to do some unit conversions here because I do not love all of my units. Let's do a quick unit conversion here. Instead of having revolutions per minute, I would love to have, whoops, that's not what I want. I would love to have revolutions per second. So what I'm going to do is I'm going to get rid of my minutes here. I'm going to put minutes on the top. I'll put seconds on the bottom. And I'm going to go with 60 seconds in 1 minute. I do a quick unit conversion here to get into revolutions per second. And when I plug this into my calculator, I get 1.3 revolutions per second. This unit conversion should make some sense to you because you should say, okay, if I'm going around, if this record is going to spin in 78 circles in a minute, it's probably going to have to do a little bit more than 1 circle per second. And that's exactly what you see. It's 1.3 revolutions per second. Now I need another little unit conversion here because I got centimeters. Now actually you don't need to show this unit conversion because it's pretty simple. We just got to get it into meters. So let's go to 0.124 meters here. Okay, and I'm looking for how fast that little book would be going. Now, sorry, I'm going to move my face. Classic. Okay, now my equation for my tangential speed, that seems like it's probably going to be important. It's going to be 2 pi r all over t. Now here's the problem. I got 2 pi because that is a constant. I got r because that was given to me. That's how far the bug is from the center of the record. But I don't have t. So I'm going to need to use another equation to find it. And the equation that I'm going to use is I'm probably going to use an omega equation. Now I got 3 omega equations. I know that omega is delta theta over delta t. I also know that omega is equal to 2 pi over t, and also omega is equal to 1 over t. And I use these different equations depending on my different circumstances. Hey, which one would you like to use? Equation 1, equation 2, or equation 3? Ah! And you say resoundingly, equation 3, Miss Wilson, because this one is the one that I use when I have revolutions per time. It takes 1 revolution in a period of time, which is how much time it takes to go in a circle. So I'm going to use this equation. Omega is equal to 1 over the period. The angular speed is equal to 1 over the period. Now I'm going to rearrange this equation here to get the period so that I can plug it back in over to this other equation. And I get that my period is equal to 1 over omega. Next, I'm going to plug in my expression for my period back over into my tangential speed equation. And I get 2 pi times r over 1 over omega, which is a little bit of a funky sort of equation here, so I can do a little bit of algebra to simplify it up and make it look a little bit cleaner. And when I do, I get 2 pi r times omega. Now I can plug in numbers here. I got 2 pi times the radius, which is times omega, which is 1.3 revolutions per second. Now, before we do anything here, stop and check this equation to make sure that this makes sense to you. Would you say that your tangential speed should probably be greater if you have a greater radius? Yeah, because the further out you're going, the bigger your circle, so the faster you're actually going. Would you also say that your tangential velocity should be greater if your angular speed is greater? Yes, because then you're accomplishing more circles in the same amount of time, so you would literally be going a greater distance in the same amount of time. So this equation looks so logical and sensical to us. This looks so very nice, and when we plug in numbers, we get 1.0. What a nice, easy number. And now let's check our units here. The units are going to be meters per second because those are going to be our units of tangential speed. But you say, wait a second, Miss Wilson, I'm doing some quick dimensional analysis here, and I see that I should get meters times revolutions per second. But you're saying only meters per second. Well, here's the good news for you people. Revolutions, and now you can like cover revolutions ears right now as we talk about it. Revolutions is actually not a very real unit. Revolutions just means number of times in a circle. Times in a circle is not a measure of, it's not a unit. For example, if I said that I had 72 oranges, then you would say, well, oranges isn't a unit. That's just how many oranges that you have. So we would say I have 72, and oranges is not a unit of measurement. In the same way, times around a circle is not a unit of measurement. So if I say I do 1.3 revolutions, that's 1.3 times around the circle. Times around the circle is not a unit of measurement. So we don't need to pay attention to our revolutions here. We just get meters per second, and so we feel nice and awesome about our final answer here of 1.0 meters per second. And there's a little practice problem for you. Now, so far, we have talked about different types of spinning. So we talked about revolutions versus rotations. We talked about the two different types of speed that you can have when you're spinning. So you can have angular speed and you can also have linear speed or tangential speed. The last thing that we're going to talk about here today is tangential acceleration. Or not tangential acceleration. Oh my gosh. Centripetal acceleration. And now, before we talk about centripetal acceleration, this is awkward and embarrassing because I keep having to get my props, but I'm going to go grab, I just have one more prop that I need to grab, and that is going to be my rubber stopper here. So we're going to talk about centripetal acceleration. Oh no, acceleration. Lovely. Centripetal acceleration. And let me go grab my rubber stopper, one quick sec. Okay, here I have my rubber stopper on the end of a string. You can see here, sorry, I'll show it a little bit closer. There's my rubber stopper, and it's just tied. It has a little string here that is tied to my rubber stopper. Okay, now here's a question for you. And you've done things like this before in your childhood, but suppose that I took this rubber stopper, suppose that I swung it around my head in a nice horizontal circle like this, and suppose that I did that at a nice constant velocity so that it wasn't slowing down like this. It wasn't speeding up and getting faster and faster. But let's say that I just had it above my head and I was spinning it at a nice constant speed. I think I might have said constant velocity earlier. I gotta be careful with my language. Suppose that we called it a nice constant speed as it's going around in a circle. Here's a question for you. As this rubber stopper goes around in a horizontal circle at a nice constant speed, is it accelerating? And you should say yes. Because even though it's not changing its speed, it is changing direction the whole way around the circle. Let's look at a picture. Okay. Let's take a look at a picture here. Here is my rubber stopper. I'm going to draw a bird's eye view. So if a bird was looking down at my head, they would see that I have this rubber stopper on a string like this. Here's my string, here's my rubber stopper. And they'd see that that little guy is going here in a circle like this, except that that was a really very, very bad circle, and I regret all of my little lines. Okay, try again, try again, try again. We can do it. Well, it's still a very, very bad circle. But you get the idea. The idea is that it's going in a circle, and I apologize for the badness of the circle. But the rubber stopper is going in a circle. I'm holding it here at the center like this. Now, here is what I want you to see. I want you to see how this guy is accelerating. We know Newton's first law, that an object in motion tends to stay in motion at a constant speed in a straight line. Suppose that this rubber stopper is being wheeled around my head like this, so that sometimes it's right there, and then later it'll end up right here, and then later it'll end up, wow, I just really wish this was a better circle. Later it'll end up right here, and then later it'll end up right here like this, so that it's going around the circle this way. Now suppose that at this point I were to, when the rubber stopper is coming around, it goes, and suppose that when it gets to right here, I let it go. Which way would it go flying? You say, well, it would probably go flying that way. Wait, actually, I'm going to do this with my small pen. It would probably go flying that way, which would be absolutely true. That's how it would go flying. Then, suppose that I continue to wheel it around in a circle. Suppose that I don't let it go. But suppose that instead I continue to wheel it around in a circle until it gets to here. If I let it go when it got to here, well then, and I let it go now, then this little rubber stopper would go, oh gosh, would go something like this way. Because it would want to be at a nice constant speed in a nice straight line. Well, then if I didn't let it go and if I kept holding on to it and then it got to here, well, then it would like to probably go, if I let it go, it'd probably like to go somewhere like that. And then if I didn't let it go there, but instead I kept holding on to it and I said, you're not allowed to go, actually you have to keep going, then it would probably keep on going here. And if I let it go right here, then it would want to go this way. Here's what I want you to see. Each of these lines represents the direction of the velocity of the rubber stopper at that point. because that's which way it would like to go if it could continue with a constant velocity. If it could keep on going in a nice constant speed in a nice straight line, the straight line would look like that, and that's the direction of the velocity. Hey, do you see that the velocity of the rubber stopper, the direction of the velocity, is always tangential to the path of the circle, which is why we call it tangential speed? Isn't that very nice? So the rubber stopper would like to, it has a velocity that has a direction that is tangent to the path of the circle, but it doesn't get to go that way. If there were no external force, this rubber stopper would love to go this way, but there is an external force because that string is putting some tension on that rubber stopper, and that rubber stopper is not going to get to go where it wants to go. Instead, it's going to end up right here. So check it out. The rubber stopper wanted to be out here somewhere, like it wanted to end up right here, but instead of getting to go there, it actually ends up having to go back here. And so it has to go back this way instead of getting to go where it wanted to go, which was to go right there. Then, when I get to at this point here, the rubber stopper wants to go that way, but because there's a string on it, it doesn't get to go there. It ends up being right here. And so, even though the rubber stopper wanted to end up somewhere like right here probably, it doesn't get to be there. It ends up right here instead. And so then it has to go this way. And it changes its velocity from what it would want to be, which is over here, to what it is, which is over here. And so it goes this way. It gets pulled this way. Sorry, I'm trying to make my arrow thicker without just drawing two lines. Okay. Then, when the rubber stopper gets here, it would like to end up somewhere out here, but it doesn't get to because there's a string. So instead it ends up right here. And so it wanted to be right here, but it gets pulled so that it's right here, so that it gets pulled this way. Hey, do you notice that the rubber stopper is always all the way around the circle? And I'm going to highlight this in a little bit of a lighter color for you so that you can see it. Do you see how the rubber stopper is getting first pulled this way, and then pulled this way, and then pulled this way? Notice, it is always continually around the circle, getting pulled back towards the center of the circle. This is the direction of centripetal acceleration. Centripetal acceleration, just like all accelerations, has a direction. And the direction of centripetal acceleration, I'll write it as AC for centripetal, is always directed towards the center of the circle. The centripetal acceleration is always directed towards the center of the circle because the object is always, it tries to go in a straight line, but then it accelerates inward. Then it tries to go in a straight line, it accelerates inward. It tries to go in a straight line, accelerates inward. Tries to go in a straight line, accelerates inward. All the way around the circle. The centripetal acceleration is always directed towards the center of the circle, which is why we call it centripetal acceleration, because centripetal acceleration means, centripetal means center seeking. That centripetal acceleration is always trying to pull it back towards the center of the circle. So the direction of the centripetal acceleration is always towards the center of the circle. Now, that means that you have some acceleration that is always making it change direction. Notice, centripetal acceleration is acceleration that makes it change direction. It's not acceleration that is speeding it up or slowing it down. It's not spinning in a circle any faster. It's not spinning in a circle any slower. It's not speeding up. It's not slowing down. Centripetal acceleration is always just a direction changing acceleration. It's an acceleration that is causing the direction to change. Now, centripetal acceleration, it has a direction that is towards the center of the circle, and it also has a magnitude. And I'm not going to derive this equation here today in this video. If you want to see it, please come talk to me because I'd love to show you the derivation. It is just absolutely lovely. But it turns out that the size of the centripetal acceleration is always equal to the tangential speed squared divided by the radius of the circle. And that gives you the size. So the direction is always towards the center, but the size is always the velocity squared divided by the r. And this should make some sense to you conceptually. Have you felt before that if you're going faster in a circle, it's harder to stay in a circle? Your acceleration is bigger to keep you in the circle? Have you felt before, the faster and faster and faster you go, the harder and harder and harder it is to stay in the circle? That's because your centripetal acceleration is bigger and bigger and bigger. You need more centripetal acceleration to stay in a circle the faster and faster and faster you go. Have you felt before that the tighter the turn, the smaller the radius, the harder it is to stay in that circle? That's because your centripetal acceleration is bigger when your radius is smaller. Smaller, tighter turns, it's harder to stay in a tight turn like that. It's easier when you got a nice big circle. You got a much lower centripetal acceleration with a nice big circle because it's not as hard to stay in a circle when your circle is nice and big. Let's go ahead and try a quick practice problem. This practice problem comes from page 236 of your textbook. And wow, this is so embarrassing, but I did forget my textbook, so I really do have to pause the video once again and go grab it. This is just embarrassing. We're going to do page 236, number 4. I'm going to pause the video, I'm going to go grab it, and then by that time we should all be on page 236, number 4. Although for you, that's going to happen like almost instantaneously. So anyway, okay, I'll see you in 1 second on page 236, number 4. 1 moment, please. Okay, here we go. Page 236, question number 4. Here's what it says. It says, a race car moving along a circular track has a centripetal acceleration of 15.4 meters per second squared. If the car has a tangential speed of 30.0 meters per second, what is the distance between the car and the center of the track? Let's go ahead and start by writing down our knowns and unknowns. We know that this car, because it tells us, has a centripetal acceleration of a size 15.4 meters per second. It also has a tangential speed of 30.0 meters per second. And we are looking for, it says, what is the distance between the car and the center of the track? We're looking for the radius of that circle. In order to do this problem, sorry, I gotta move my face. Face, go away. Okay, in order to do this problem, we are going to start with our original equation. We say that the centripetal acceleration is equal to the tangential speed squared over the radius. Then let's rearrange for the radius. To rearrange for the radius, we get that the radius is equal to VT squared all over the centripetal acceleration. And then we can plug in numbers here. We plug in 30.0 meters per second divided by centripetal acceleration, which is 15.4 meters per second. Squared. My gosh, that was embarrassing. Plug it into our calculators, and we get something like 58.4 meters for our final answer. And that's all for today, folks. Today we talked about uniform circular motion. We talked about 2 different ways to spin. We talked about 2 different ways to talk about your speed when you're spinning, and then we talked about centripetal acceleration. When we talked about centripetal acceleration, we talked about the direction of that centripetal acceleration. It's always towards the center of the circle. That's what keeps something going in a circle, is that it has inertia wanting to keep it going at its constant velocity, but then that centripetal force, that centripetal acceleration pulls it back in. Then we learned the equation for centripetal acceleration, and we tried a practice problem. And that is all for today, folks. I hope you have a wonderful rest of your day, and I'll see you all next time. Bye, good people.